generation, which is kind of new chapter. We never touched it before. So, as always, I will actually head over the lecture to Yusa to actually start, like today's lecture. Okay, off to you.
All right, thanks, Daniel, for the introduction. Can you guys hear me?
Yeah, we can.
All right, thank you. So today I'm gonna talk about the natural language generation, and me and Zoe are gonna follow this structure as follows. So Zoe is gonna firstly gonna have a little recap of what we've covered before, the language modeling and the decoding algorithms, the greedy search, beam search that we already have covered, and the new technique called sampling, decoding algorithm. And then we're gonna enter in the natural language generation to talk about the few tasks it has, the summarization and the evaluation matrices called ROUGE. And also then we are gonna talk about the neural summarization and with its coping problem. And then I'm gonna talk about the dialogue, task, the storytelling, and poetry generation, and use it based on this structure, and also have a little more discussion about the evaluation matrices and current research of the neural language generation research. So unfortunately, Zoe has made a video, so I'm gonna firstly present this to you guys, and please feel free to interrupt or comment at any time, because this topic is pretty new, and all the topics are mostly based on new papers being published in the recent less than 5 years. So if anyone has relevant experience, please disrupt and let's discuss. So I will just play this video share records. Sorry, am I gonna need to refresh this?
Hi everyone, thank you for coming to this lecture.
Sorry, just to check, can you guys hear her voice?
Yeah, pretty good.
Okay, perfect. So I will just play this, and let me know if anyone has any questions.
Today our topic is natural language generation. My name is Zoe. I'm currently a second-year master's student at the University of Toronto. Unfortunately, I cannot be in this live stream today, and I'm asking Yusa to help me share this video with everyone. And I guess that's less stressful for me too. So let's get started. First of all, let's talk about what is natural language generation. So natural language generation refers to any setting in which we generate new text. It is a subcomponent of machine translation, summarization, specifically the abstractive one, but later we'll talk about hybrid extractive, abstractive one. Dialect, which is pretty intuitive. It contains like chitchat, task-based dialogue, non-task-based dialogue and stuff. And also creative writing, for example, story writing, poetry generation, free-form question answering. In other words, the answer is generated by this natural language generation. So it's not extracting from text or existing knowledge base, and also image captioning, etc. Let's do a quick recap. So previously we talked about language modeling, which is the task of predicting the next word, giving the word so far. So basically you're trying to predict the probability distribution of YT, giving the previous T minus 1 words generated. And any system that produces this probability distribution is called a language model. And if that system is an RNN, it's called an RNN-LM. Also, we talked about conditional language modeling, which is the task of predicting the next word, given the word so far and also some other input text. Another input x. So basically you have this probability distribution of yt conditioned on the previous t-1 words generated and also some input x. Some of the examples of conditional language modeling tasks can be machine translation, where you have this input of a source sentence and you want to have this target sentence generated. And also other examples are like summarization, where you have this input text as input x, and also you want to get the result of a summarized text. Also another example can be dialogue, where you have this input text of this dialogue history, and you're trying to generate this y, which is the next utterance. Let's do a recap of how do you train a RNN-LM. So we have this example here as a neural machine translation. The thing that we need to remember is that we feed the target sentence into this decoder model. So basically it's called teacher forcing. We feed the goal target sentence into the decoder regardless of how the decoder predicts. So yeah, just remember we have this teacher forcing here. And also let's do a recap of the decoding algorithm that we learned. So the problem is that once it's trained their conditional language model, how to use it to generate text. And the answer is we use a decoding algorithm. The decoding algorithm is an algorithm you use to generate text from your language model. Previously, we've learned two decoding algorithms. One is called greedy decoding and the other one is called beam search. So for greedy decoding, it's a really simple algorithm. On each step, you just take the most probable word using Softmax. So here you have key, and then you just put this key generated by Softmax into the next step as an input. And you keep going until you produce the end label or you reach some max length. And the problem is due to lack of backtracking, which means that once you make a mistake in one step, you cannot go back. The output can be poor. That means that it can be ungrammatical, unnatural, or nonsensical. Let's look at the beam search decoding. It is a search algorithm which aims to find a high probability sequence. It doesn't have to be the optimum sequence. And they do this by tracking multiple possible sequences at once. The core idea is on each step of a decoder, the decoder keeps track of the k most probable partial sentences. So they're not keeping track of the full sentence, but the partial sequences. And for that, we call them hypotheses. The k here is the beam size. So basically the decoder expands hypotheses and then trim to keep only the best k. And after you reach some stopping criterion, you choose the sequence with the highest probability. And that's factoring in some adjustments for length. Let's take a look at this example. So here we have a beam size of k equals 2. So for here, you can see that the decoder is keeping track of hit and was, which has the higher probabilities here. And then later on, you're just keeping track of here and here, and then later on, when it stops, you can see this green lighted sentence. That's the optimal sentence, but it doesn't necessarily is the So here is the high probability sentence, but it doesn't necessarily need to be the optimum sentence. The professor actually gave us a really good example of what the world thinks of beam search, I guess. So basically, when she was watching Westworld, she saw this user interface. She saw this AI looking at this interface where here there's this like dialogue generation. And it really looks like beam search. So it's kind of fun. And also she saw those fun terminologies like knowledge base, forward chaining, backward chaining, backward propagation, and also fuzzy logic, algorithm, and neural net. So that's actually pretty cool. Yeah. And then let's take a look at what's the effect of changing beam size k. So basically, if you have a smaller k, you have similar problems to greedy decoding. If you have k equals 1, it's just basically greedy decoding. So basically, you have problems of your results being ungrammatical, unnatural, and incorrect. And when you have a larger k, it means that you consider more hypotheses. So basically, increasing k reduces some of the problems above as the greedy decoding problems, but it's also more computationally expensive, and it also introduces other problems. For example, for neural machine translation, increasing k too much will decrease the BLEU score. So basically, it's primarily because if you have a larger k, the Bing search will have more candidates to choose from, right? And normally, when the shorter responses, they're like the safer choices. They would have a higher probability, but they wouldn't like necessarily make sense. So that's the problem with neural machine translation. That's why they have a lower BLEU score. It doesn't include the key words that needs to be included, and sometimes when you increase the k, it can even produce empty translations. Another problem is in open-ended tasks such as chitchat dialogue. So the large k can make output more generic. What does it mean by more generic? Let's take a look at the next slide to see an example. So basically here, we can see that a human chit-chat partner says, I mostly eat a fresh and raw diet, so I save on groceries. That's pretty cool, right? That's a good chit-chat dialogue to initiate. And then when you look at the Bing size equals 1, the model would respond, I love to eat healthy and eat healthy. That doesn't really make sense, but that's actually quite relevant to what the human previously said. So it's more on topic, but it's not very, doesn't really, like, it doesn't seem to be very humane, and it's really bad English. And when you increase the Bing size, let's look at some of the examples here. So the machine would respond, what do you do for a living? So it's really correct. It's really correct response, right? But it's really generic, and it's really less relevant. So it's more of a safer choice for the machine to do so. But it's definitely gonna affect the whole conversation, because the human would be like, oh, this doesn't make sense at all. So this is not. You need to find a balance basically with the Bing sites so that you don't have a really ungrammatical answer, and you also don't have this really safe and stupid answer that doesn't make sense while looking grammatically correct. Now, here are some decoding methods that we didn't previously cover. It's called sampling-based decoding. So there are like two different versions. The first one is called pure sampling by the professors from Stanford. Why though? It's because it's just pure sampling. So on each step T, the decoder would sample randomly from the probability distribution T, PT, to obtain the next word. So it's kind of similar to greedy decoding, but it samples instead of using the Softmax. The other method is the top-end sampling. So basically on each step T, the decoder randomly sample from PT, restricted to just the top and most probable words. It's very much like pure sampling, but it's truncating the probability distribution. If you look at it, if n equals 1, it is greedy search. If n equals b, it's pure sampling. And also increasing n, you can get more diverse and risky output. And when you decrease n, you get more generic and safe output. So basically top n sampling is usually called top k sampling, but here we're saying it's top m because we're trying to avoid the k that was used to represent Bing size in the previous slides. There's also top p sampling. So basically, you're randomly sampling from PT and restricting to just the top P portion, the most probable words. So it's not top N, but top P portion. Again, it's like pure sampling, but it's truncating the probability distribution. Seems like it's better than the previous methods. There's also a technique that we should be aware of. It's called softmax temperature. So basically, when you're using softmax, on each time step T, the language model computes this thing by applying the softmax function to vector of scores. And you can apply a temperature hyperparameter tau to this softmax formula. When you raise the temperature tau, this formula becomes more uniform, the softmax becomes more uniform, and thus it provides more diverse output. The probability is spread around the vocab. And when you lower the temperature tau, PT becomes more spiky and thus less diverse output. So it's centered around the top words instead of like looking through the whole vocab. So basically, this is a good technique. It is not a decoding algorithm, but it's something that you can combine with a decoding algorithm to achieve your goal. For example, controlling on the diversity of the results. So in summary of the decoding algorithms, we have 3D decoding, beam search, and sampling methods. 3D decoding is a simple method. It gives really low quality output. And for beam search, it searches for high probability output. It's especially with high beam size, it delivers better quality than greedy. But if this beam size is too high, it can return high probability but unsuitable output, like the generic and short ones. For sampling methods, they're a way to get more diversity and randomness. I think for pure sampling and probably some of the more diverse uh, top K or top P sampling methods, it's good for open-ended creative generation. For example, when you want to generate something like poetry or stories, because there's this diverse and risky results generated. And for top and top P sampling, it allows you to control diversity, which is pretty cool. And a really important thing to note is that softmax temperature is not a decoder algorithm. It's a way to control diversity, and you can combine it with the decoder algorithm. Now let's move to section 2, NLG tasks and neural approaches to them. So let's look at the task definition of summarization. The task is when you're given input text X, you write the summary Y, which is shorter and contains the main information of X. The summarization can be single document or multi-document. For single document, it means we write a summary Y of a single document X. For multi-document, it means that we write a summary Y of multiple documents X1 to Xn. So typically, we have a spread of X1 to Xn documents, but we expect it to have overlapping documents. We expect it to have overlapping content, right? So it makes sense because, for example, if you have like 10 news articles that are kind of that have like kind of similar content, you want to try to like summarize them so that you can have a comprehensive view of all the contents and they're centered around the same topic, right? So it really makes sense. So with single document summarization, let's look at some data sets. We have like data sets with different source documents of different lengths and styles. We have this gigaword data set, which contains a lot of first 1 or 2 sentences of news articles. Basically, the task is to summarize those first 2 sentences into headline. So basically, it's just sentence compression. We also have a data set that's about Chinese microblogs. So you have a short paragraph and you want to summarize it into a sentence. There's also this New York Times, CNN/Daily Mail news article data set where you have lots of news articles and you want to summarize them into 1 or multi sentences. There's also WikiHow data set. Basically, the idea is to summarize, to get summarized sentences from full how-to articles in Wikipedia. There's also a new data set, 2 new data sets, which is Exam and Newsroom. Basically, you want to write 1 sentence summary for articles. There's also this different but related task called sentence simplification. The idea is to rewrite the source text into a simpler way, which means you're gonna translate those difficult to understand words into simpler words so that people will understand it easier. And normally when you try to write stuff into a simpler way, it's sometimes shorter. So it's kind of like a summarization problem too. So we have simple Wikipedia, which is dataset, which is which whose task is to summarize the standard Wikipedia sentences into simpler version, basically making the sentence easier to understand, right? And there's new Cella dataset, and its aim is to write easier to understand versions of news articles for different children of different learning levels. So it's kind of cool. We can look at summarization as two different main strategies. One is extractive summarization, and one is abstractive summarization. So for extractive summarization, it's basically like when you're using a highlight pen to read through a textbook. So basically, you're just selecting parts from the original text, and you're not generating anything new using your brain. It's very easy, but it's actually really restrictive because when you have a really long sentence, you can just select parts of it. But as humans, we know how to generate summarization and rephrase them by our brain, right? So actually, when you're just extracting stuff from the original text, it limits your ability to do that. And in that way, we have abstractive summarization. So it's like you're using a pen to write a summarization of an article. You have this brain power to make it shorter and also paraphrase all the contents to make it clear, precise, and really, really short. So here we're actually generating new text using the natural language generation techniques, but it's definitely a more difficult task. Let's first take a look at the extractive summarization's pre-neural net phase. So the pre-neural net summarization systems were mostly extractive. Like pre-neural machine translation, they typically had a pipeline. So the first phase is content selection, which means you choose some sentences to include from this original text. The second phase is information ordering. You basically choose an ordering of the sentences that you decided to include in the first phase, and then you feed it to the third stage, which is the sentence realization. Basically, the system edits the sequence of the sentences. For example, it simplifies the sentences, it removes parts that are redundant, and it also fixes continuity issues. One good example here is that, for example, if you're trying to summarize from different documents, you would want to, after grabbing all the relevant sentences that you want to include, you want to rearrange the sequence, right? So that it makes sense. And also, for example, when you make the sentence at the beginning of the whole document, whole summarization document, and it refers to someone as she, you would probably want to change that because you didn't even mention her name first. So basically, you have all those things that you need to change in the third phase, which is the sentence realization. So there are two methods used in the content selection algorithm. The first one is called sentence scoring functions. It can be based on two things. First, you can base it on the presence of topic keywords. And the way you compute those topic keywords is fairly simple. For example, you can just use CFIPF to compute it, right? And also, you would try to score the sentence based on where the sentence appeared in the document. It's also fairly intuitive. So, for example, when you're reading a news article, normally at the beginning of this document, it contains more important sentences that are more like summarized. So those are the sentences you might want to score with a higher score. And also, there's a different method for content selection, which is called the graph-based algorithm. It will view the document as a set of sentences, and the sentences are considered as notes. And you would also get edges for each sentence pair. So the edge rate is proportional to the sentence similarity. And by using the graph algorithm to identify sentences, you can kind of understand like which sentences are central in the graph, and then you would score those sentences with a higher score. ROUGE is a very important evaluation metric for summarization. So ROUGE stands for recall-oriented understudy for guessing evaluation. Like Blue Score, it's based on n-gram overlap, and um, the researchers probably named ROUGE as ROUGE because they wanted to match it with Blue. The difference is that ROUGE has no brevity penalty, and ROUGE is based on recall, while Blue is based on precision. So basically, it's not difficult to understand that precision is more important for machine translation with the metric Blue, right? Because you might not want to include all those non-relevant words into the translation. And also, they would add this brevity penalty to fix under translation, which means a shorter sentence probably won't contain all the needed uh, keywords for this translation. And recall is more important for summarization because you want to include all the important content into the summarization, right? So you don't want to miss some of the key parts. And normally you would have the max length constraints so that you can have kind of the balance between the length and also like the key components you want to include. Um, there's a weird thing though. So for a root score, often there's also F1 score included. It's kind of weird. And for blue score, it's normally reported as a single number, which is combination of the precisions for n equals normally 1 or 2 and 3 and 4. Um, for ROUGE, the scores are reported separately for each n-gram, and the most commonly reported ROUGE scores are ROUGE 1, which is for unigram overlap, and ROUGE 2, which is for bigram overlap. And also, researchers would also look at ROUGE L, which stands for the longest common sequence overlap. And it's important to mention that there is a convenient Python implementation of ROUGE. So I guess everyone needs to take a note of that. So let's look at research regarding neural summarization. So in 2015, ROUGE et al. Published the first seek-to-seek summarization paper. So the idea is that the single document abstracted summarization is kind of like the translation task. Thus, the researchers apply standard seek-to-seek attention neuromachine translation methods into this and achieved pretty good results. They did the experiment on the gigaword dataset, so it's kind of really intuitive to understand because we can remember as I mentioned before, the gigaword dataset contains a lot of data, which for each data is like the first one or two sentences of a document, right? And then you want to compress this one or two sentences into a headline. It's kind of similar to your machine translation, where you have this input sentence, which is normally like one line of sentence, and then you want to get a result of also a one line sentence. So it's kind of similar as in the data structure, right? So that's why you're like doing this with this idea of this newer summarization can be understood as a newer translation problem. And also, since 2015, there have been lots of developments regarding different aspects. For example, researchers have been making efforts in making it easier to copy for the models. What does it mean by copying? So basically, for summarization, sometimes it's just easier to copy words and snippets from the original text into the summarization, right? So it's actually like super simple idea, but it's really difficult to achieve. That's why the researchers have been doing this study. And they were also trying to prevent too much copying because in that way it's not summarization anymore. It's basically just copy pasting. Researchers have also done research regarding hierarchical multi-level attention and also coming up with a more global content selection, which would definitely help with the summarization, and we will explain that later. Researchers also did research regarding reinforcement learning to directly maximize ROUGE or other discrete goals because directly maximizing ROUGE score is kind of non-differentiable And some of the researchers also worked on resurrecting pre-neural ideas such as graph algorithms for content selection and working on them into neural systems. Let's take a look at the copy mechanisms. So for the seek-to-seek attention systems, they're really good at writing fluent output, but they're really bad at copying over details, like real words correctly. So this copy mechanism uses attention to enable a seek-to-seek system to easily copy words and phrases from the input to the output. Clearly, this is very useful for summarization, as mentioned before, and allowing both copy and generated method gives us a hybrid extractive abstractive approach, which is kind of cool. There are other papers proposing copy mechanism variants, and we're going to talk about an example from the Stanford professor later here. So basically, this is just one example of how to do a copying mechanism. So for each decoder step, the researchers calculated p-gen, which is the probability of generating the next word rather than copying it. And then they would try to use this p-gen, which is a scala, to combine the generation distribution with copying distribution. So the idea is this output probability distribution is a combination of p-gen times the generation distribution, and also combined with the copying distribution, and also considering the part that you're attending to, and thus getting this copy mechanism out. But there is this big problem with copying mechanisms because they copy too much normally. So they will mostly give long phrases and sometimes even the whole sentences, which is not good at all. So what should be an abstractive system now collapses into a mostly extractive system, which is not smart at all. And another problem is that those copying mechanisms are really bad at overall content selection, especially if the input document is long. So basically, the problem is that there's no overall strategy for selecting content implemented into the system, right? So they would just look into each sentences and figure out which part of the sentence to select, and thus summarizing on those parts. And this is actually very expensive to do and not very intuitive. So the idea later is to get a strategy to incorporate this content selection phase before doing the seek-to-seek attention model. So let's remember that the pre-neural summarization had separate stages for content selection and then surface realization. But here in this standard seek-to-seek attention summarization system, these two stages are mixed together. As I mentioned before, so on each step, we would do selection with attention, and then we would do surface realization. So it's really bad. The solution is bottom-up summarization, and it was published in 2018. So basically, the researcher incorporated the idea of content selection and put it as the first stage. They used a neural sequence tagging model to tag words as include and don't include. And then they would use this bottom-up attention stage. The seek-to-seek attention system can attend to words tagged as not include. So basically, they're applying this mask, and then the attention cannot be put on the masked words. It's a very simple but effective method. It provides a better overall content selection strategy, and it also kind of just help with the copying too much problem because the system can now cannot look into the longer sentences because some of the words of the longer sentence are masked. So basically, there's no longer system, and there's less copying of the longer systems. There's no longer sequence, and there's thus no copying of those longer systems. Longer sequences, oh my god. Yeah, longer sequences, sorry. And thus we can have a more abstractive output because now the system needs to look into the different snippets of a single sentence and try to generate a sentence out of it. Let's look at the neural summarization with reinforcement learning. So basically, in 2017, Paulus et al. Published deep reinforced summarization model. The main idea is to use reinforcement learning to directly optimize ROUGE score. Previously, researchers used standard maximum likelihood method to train, but they cannot directly optimize on the ROUGE-L because it's a non-differentiable function. So here's an interesting finding from the paper. So basically, when they tried to use reinforcement learning to directly optimize ROUGE-L and back up that score into the model, they definitely achieved a higher ROUGE score, but a lower human judgment score. Why though? It's because they're basically trying to game the system, right? They're trying to game targeting just the scoring of one single metric, and thus the model definitely give them that result, but it's actually very counterintuitive for humans to understand. So that reinforcement method didn't even beat maximum likelihood regarding readability here, and it was beat like really badly. So they used a really intuitive hybrid approach, and it actually did a really well job in both readability and relevance. So the next part, which is dialogue, I'll pass it to Lisa, and thank you everyone for listening to me babbling.
All right, thank you guys for watching this. So do you guys have any comments or questions regarding Zoe's presentation? All right, then I will just take over on my part to talk about a few other natural language generation tasks that we're gonna solve. So first, I'm gonna talk about the dialogue problem. So there are two types of dialogues. One is a task-oriented dialogue, and the other is a social dialogue. So as for the task-oriented dialogue, it has the assistive, like customer service recommendations. So basically, it's like Siri. So the questions you ask them, the question you ask your cell phone to do, and cooperative, two agents are solving problem together through a dialogue, and adversarial is like competing with each other in a dialogue, and also in a chitchat situation, also during the mental health therapies, and these are kind of the dialogues that we have. So when solving this problem, it has a pre and post neural dialogue time. So as for the pre-neural dialogue system, people were mostly using the predefined templates to solve this and retrieve and appropriate response from a corpus from the of the response. And after 2015, many papers have been coming out to using the seek-to-seek models to on the dialogues, and reaching out the more open-ended, the free-form dialogues. And these are some papers that have been mentioned in the following slides. So with the during this neural dialogue solving time, we were using the seek-to-seek plus attention models to solving these problems. But it has a few problems with this. The first one is the genericness and boringness. So for example, this dialogue would mostly leading to a same answer, same sentence or conversation until the end. So it won't change anymore. And it has been mentioned in this paper. And to fix this problem, the most easy way to is to upweight the rare words during the beam search. So we could search in the decoding algorithms to more differentiate conversation. And the other way is to use sampling decoding algorithms rather than the beam search, as Zoe previously mentioned. It could also solve this problem. And also, we have another way of conditioning fix on this problem. So basically, condition the decoder on some additional content, such as the specific content word that we want to attend. So the dialogue could go through that direction instead. And the other way is use a retrieve and refine model rather than generate from scratch, because you already used the human written utterance to train a model. Then the dialogue could follow that direction instead of generate the entire dialogue from scratch. So besides, it has another problem called irrelevant response. So this dialogue could not be relevant to what begins in the beginning. So the solution is to maximize the mutual information between the input and response. So we add the penalty here to penalize the generic response in the objective function, so that the model is used is to penalize the generic sentence, the conversation in the end. And we also have a repetition problem. So the most simple way to solve this problem is by blocking the repeating engram. So it's pretty effective in the most cases. And there's another complex solution by training a converge mechanism. So you just prevent the attention mechanism from attending to the same word multiple times, and therefore resolving this repetition problem. And in the meantime, we add a training objective to discourage the repetition. And also, we finally, the last problem is lack of consistent personnel. So there's a technique introduced in this by the team of Lee, and they were trying to embed the personas as an embedding to our dialogue training, so kind of solve this problem. And another task that NLG has is negotiation. So for example, in this paper, it has introduced a problem of two agents negotiating with each other of how to divide a set of items. So each item has different value functions for the items, and the agent's task is to negotiate and find their most optimal solution to them, and finally making an agreement. So by going through the conversations. So the problem with this seek-to-seek model is that although the conversation could go fluent, but in this negotiation circumstances, it would be a strategically poor dialogue agent. So in this case, they use the reinforcement learning to optimize the discrete forward by firstly letting the agents to play with themselves during the training time, so that they could be optimizing their objective of getting the most optimal negotiation plan for themselves. So this is how the negotiation dialogue would look like. And during the dialogue, it could has both ways of answering the questions. And finally, it will lead to a final score. And in this case, the score of 9 would be the optimal communication technique for them. So the model would choose between the possible responses by computing the rollouts as the just the scores in this picture here. So there's another hierarchical text generation technique, but it has been skipped in the lecture, and I haven't been able to look at the paper, so I don't think I pretty much understand everything here, so I'll just skip it either. So then it comes to the another NLG task. It's called the conversational question answering. So basically, people are going through their conversation, and we could, in the end, ask the computer to see what's the answer between their conversations. So this problem is requiring the answers to be written abstractly. So basically, this is a task, and I think more details is in this paper as well. So another interesting topic for NLG is storytelling. So it has two main ways of doing this. So the first one is going through making an image as an input, and then the text is gonna generate it. And the other one is going from a prompt. So we enter what we want the system to generate, the topics, the main words, and then it would generate the story for them. So for this case, the image generation, we were using the Taylor Swift lyrics as a training corpus. And then the model is going through this picture and the language modeling separately, and finally generating the explanation of the picture with the style of Taylor Swift songs. So, but in this case, the most difficulty is the lack of parallel data, because you might have a lot of pictures, but not much pictures has a designated, stories with them. So the solution is to use the technique called common sentence encoding space by training the image and the lyrics separately, as I said before. So we were using the skip thoughts vectors to generate the general purpose sentence embedding method. And so basically training the pictures and the lyrics separately, and finally put them together to finish this task. So talking with another way of generating a story is from writing prompt. So as example showing in this paper here, we were input the 3 words, so these 3 guys, and then we generate this story like this. So in this paper, in this example, we were using a complex seek-to-seek prompt-to-story model, and it is convolutional based. And the good point is like it is faster than the RNN seek-to-seek, and it is using the gated multi-hat, multi-scale self-attention to using the self-attention to capturing long-range contents, as we discussed in the last lecture. And the gates are allowing the attention mechanism to be more selective. And also different attention hats are being used to attend at different scales, so that we could retrain different information and in different scales. So what's special about this model is it is using the pre-trained seek-to-seek model, and it is using it trains the one seek-to-seek model in the first, and then train another seek-to-seek model to access the hidden states of the first seek-to-seek model. So the idea is that the first model would learn the general language modeling, and the second would learn the conditions on the prompt, the input in the prompt. So as a summary for this model, it is generate the impressive results, and the story it generates related to the prompt, it is diverse enough, and it's not generic, and it has stylistically, dramatically. But on the other side, so it is mostly descriptive, and it is staying on the same idea without moving forward. So this story just stays there and couldn't move forward. So this is a problem with using this model as a storytelling model. So then it comes to the neural storytelling. So after 2018, there's a lot of workshop. So you guys can check out this website, and there are most advanced storytelling groups discussions here. And they hold a competition of generating a story with a sequence of 5 images. So which is a pretty interesting competition. So the challenges with the storytelling problem is that the stories it generates could sound pretty fluent, but in the meantime, it is non-sensational, it's not coherent plot in the bigger picture. So what is missing is actually comparing with the language modeling, it was more, the stories are more like a sequence of events instead of language modeling, which is the sequence of words. So you need to have a bigger picture of how things are going through, instead of just on the word side. So we need to think about the following things to make the stories sound more reasonable. So we need to think about the events, the characters in the stories, and the states of the world of the stories, as well as the narrative structure. So a whole bigger structure than the language modeling itself. So there are several techniques to bringing the stories, the events into the storytelling. So the first one is called the event-to-event story generation technique, which introduced by Martin's team. So the basic idea is to extract the events from the input, and then generate the next event based on the event it extracted, and finally it generate the sentences from the events instead of only the words, just like the language modeling. So the structure of story generation is like this. Sorry, this is another technique called the structured story generation, which is brought by the fans team. So this way, it is bringing the stories of the event by action plan with semantic role labeling. So it is just tagging all the verbs and relationship between different entities and putting them into the model, and then could let the model to generate the story based on those relationships. Still, instead of the basic words, it is implementing the relationship between different entities. And there's another technique called tracking events, entities, and states. This is actually a neural language understanding task by tracking all these events, entities, and states within the human languages. And so this is pretty difficult because instead of generating the open domain stories, we also need to track all the states. Basically, it's a relationship between all the characters and events in the entire story. So there's another way to solve this, introducing the events to the stories. Is called the tracking world state while generating the recipe. So it explicitly tracks the state of the ingredients and decide what action to take the next. So the main idea is here. So it predicts the states of the story, such as the location, the temperature being mentioned in the story, and if it's a claim, and basically the whole bunch of the states being mentioned in the story. And then it could predict what's going to happen next. So the story won't just depend on those words, but the entire system on the other hand. So as for the neural language generation task, there's another interesting application. It's called the poetry generation. And this is mainly based on this guy's projects called Hafiz. And these two papers are fully illustrated how it works. So basically, it is making the desired rhythm within the poetry as a constraint into the model, because the poetry has different character than other stories and generation tasks, because it must follow some kind of rhythm. And therefore, it is requiring the models to only explore the hypotheses that fall within the finite state acceptor, which defines all the possible sequences that only obey the desired rhythm constraints. And in this case, the full system would look like this. So when the input could be some kind of topic word, and the model would get a set of words related to that topic and identifying what could be the remaining topical words, and then just assign all those words to the end of each line. So basically that's how this poem will work. And generating the poem using the RNN language modeling constrained by the rhyme constraints. And it is training, it is backward training from right to left, because we know that all those words at the end has already been determined in the beginning. So there are three improvements to this poetry generation task. So the first one is what also being mentioned in this paper, because they were making the system interactive and user controllable. As you can see, people can change the sentiment of the poem, the repetition, and does any curse words should occurs in the poem, and different poem could just generate it using this system. So another improvement was brought by Lao's team. So it's called the deep spears. So the main idea is like they were using three different models. The one is a language model, and the second is a pentameter model, and the third one is called the rhyme model. So in this specific poem application, they were trying to learn jointly of the three models as a multi-task learning problem. So overall, the meter and the rhyme is like relatively easier to get trained, but this system had his hard time finding the emotion and readability of the poem. So there's another improvement brought by the Goose team. So it's called the non-autoregressive generation of neural machine translation. So in this case, the translation doesn't go from the left to right. Instead, it is paralleling the decoder at the test time. So we're using the transformer in this case, which is clear is that using the transformer would make the system more efficient, and it also has intriguing in the text generation point of view. Do you guys have any comments or questions regarding these three applications towards the poem, storytelling, and negotiation? All right, perfect. So next I'm gonna talk about the natural language generation evaluation. So this is pretty important because we need to find a way to evaluate how our models works. Otherwise, we cannot optimizing things. So as we know before, we've already introduced a few word overlap-based matrices like blue, ROUGE, Meteor, F1, etc. But for example, bring back our memory to the blue matrices, it has a few limitations. So the first one is it only works well in the corpus level. For example, when there's zero precision scores in the entire, in that case, it would lead to a zero blue score, so which totally doesn't make sense. And the second limitation is that it is limited to several references, so it doesn't work really well considering the bigger picture of the reference that doesn't include it, and which is makes it not sufficient to be determining whether a translation model is good or not. So this problem would be more difficult in this summarization problem, because this problem is more open-ended than translation. And in this case, ROUGE would reward extractive over the abstractive, and the neural summarization is actually trying to be more abstractive than extractive, so which comes into a dilemma in this case. And as you can see, the blue score is not correlated with human score in this summarization problem. And different groups of human scores instead could be correlated with each other, which means that the blue score and is not a good matrix to define whether that dialogue is good or not. So then brings up to another question. So can we use perplexity as matrices to evaluate whether that dialogue, I mean, analogy problem is good or not? So the problem with perplexity is that it is only showing the how powerful the language modeling is, but is not it has nothing to do with neural language generation. So it is only thinking, it can only tell how that next word is related to the previous one, but not overviewing on a bigger picture. So there's another comment on word embedding. So people are thinking whether we can using similarity of word embeddings to capture the semantics in a more flexible way of determining the entire generated words. But in this case, it has nothing to do with human judgments. So maybe on the machine, it makes sense, but when you read it, it could be nonsense. And we need automated evaluation matrices to be as a proxy of human judgments as a evaluation matrix for the generation task. So what we want the automated evaluation matrix does is to review the fluency and the correct style, the diversity of the story, the generation, and the relevance to the input, and also some simple things like length and repetition, and also to test them on the few specific tasks like compression and summarization. So basically, this is how we want our automatic evaluation matrices to do. But however, we're not having single matrices that could be evaluating the overall quality of the generation. But thinking this way, we can trying to optimize one or several of these criteria so that we could tracking some important qualities that we cared. And on the comparison to the machine evaluation, we let us talk about the human evaluation. So the people are thinking that human evaluation could be good in this case, but usually it is slow and expensive, and it is difficult to implement because people are like inconsistent. When you are tired, you might have a different opinion towards our words, and people could be illogical and lose concentration while it gets tired or sleepy. And people can also misinterpret your question. So they're thinking in another way instead of the test team is required them to do. And sometimes they couldn't even explain why they made the decision or made that comment. So what being mentioned in this paper discussing how this human evaluation of controllable chatbots works. So it is saying that there are several good questions to ask human beings to as a I mean, the question asked them to evaluate how that model works is like the first one is how do you find this conversation goal and the engagedness to the user, and also this kind of following problems. But this human evaluation has some problems, like in this specific paper which introduced is like it is really subjective, and it is misunderstanding a lot of questions, and also respondents have a different expectation. So the overall quality may depend on multiple factors. And then the author of this paper was thinking to separate the important factors so that they in the end are contributing to the overall chatbot quality. So she was introducing some from the lowest level, such as the reputation, the question asking, and the specificity, and then to the final level of how do you think that question is, like the humanness and engagedness. And the interesting finding in this case is that the engagedness is pretty easy to identify, and as a evaluation matrix to maximize, because it is easy for the machine to recognize does that sound like a human. But on the other side, the humanness, it is really hard to maximize, because it is just like the Turing test. It is really hard to find if that man beats the machine, or I mean, they outperform each other by making a more clever machine. So this is a problem with the evaluation matrices that found in this paper. And there are several other new things are happening in this neutral language generation evaluation world. So the first one is called the corpus level matrices. So the main idea is that applying on each example in the data set independently. So the evaluation matrices is focused on different examples separately instead of generally treating the evaluation matrices. And also the world is talking about the diversity and safety trade-off. And there are also an interesting one called gamification, because sometimes we could make human evolve free by making this task as a game. So for example, talking to a chatbot. So human would provide supervision and implicit evaluation for free, and people are having fun to just making the system as a game. Also, the world is thinking about using a adversarial discriminator as evaluation matrices. So basically, letting the discriminator to distinguish if it's a human text or artificially generated text. So in this case, as another evaluation matrices. So let me finally discuss some new natural language generation research, these trends and tips from the instructor of this course. So there are three different trends that in this narrow language generation world. So the first one is people are trying to incorporating the discrete latent variables, which means that using by putting the tasks, entities, and events of the story of the text into the model. Just as I mentioned before, in this which is previously the neural language understanding task, but people are finding this is a really good way to solve a problem like storytelling or other task-oriented dialogue problem. And the other trend is the people are using alternatives to left and to right generation with parallel generation or iterative refinement and top-down generation, and this kind of different ways to generate words. And finally, trend is that instead of maximizing the likelihood of training, so we can also focus more on the sentence level instead of the word level objectives. So basically thinking about the bigger picture. So although that NLP and the deep learning combo has been developed really well in the past 5 years, but the NLG is still quite wild word, because we're facing the problem of the lack of evaluation matrices that I previously mentioned. So we haven't got a really good automated evaluation matrix to evaluate how our model does. And here are some interesting NLG communities that you guys can check it out. So should be really interesting. And these are several tips from our instructor, and which is that the more open-ended tasks like word generation is like harder than the previous translation problem that we faced. And also we could thinking about the specific improvement instead of overall improvement while we're not having a really good evaluation matrices. And also you should think about your output a lot. And if you are having a ultimate matrix, which is really good, but I don't think we have one right now. Yes, I guess that's everything being included in that lecture. And this part is pretty interesting of our instructor's chatbot, and you guys can check it out. So thank you guys for hearing. Do you guys have any questions?
Thank you, Isa. That's a very nice lecture. Any questions from the audience right here? No questions. If we don't have any questions, then let's call this a day. And huge thank you to Zoe and also Isa for the lecture. Really informative and really straightforward and very easy to understand, actually.